First attempt glitches here. Okay, so get started here. So, a couple things I want to mention. Switch off this real quick. There we go. So I put up that next kind of smart book if you want to look through that. We'll probably start some probability stuff on Friday, but really it won't be until next week that we dive into it. I've got kind of that Excel homework and that Connect assignment, which are due at the end of this week. So if you're looking at that Connect assignment, a lot of it, we'll go through some of it today to kind of help you finish probably the last 4, 5-ish questions. Maybe touch a little bit of it at the very beginning of class on Friday, although I think we should get through what we need to today for you to get on and get that done. If not, we'll see where we're at the end of today's class. I might push that due date on the Connect assignment to the end of the day on Monday, right, instead. So I would kind of focus on that Excel assignment, make sure you get that done by the end of the week. We definitely covered all that last week. And then I should get those individual assignments. You should see your grades start popping up this afternoon in between classes. It was kind of my plan for today is to get all of those graded. Okay. So that's kind of where we're at. Are there any questions before we kind of jump into material today? Just kind of, I was trying to go through some housekeeping stuff. So everybody have a good Labor Day weekend. Yeah.
Are we going to Q1
Q1, Q2. Oh, yeah. So I think, yes, we should get there today. If we don't get there today, we'll definitely get there on Friday. And that's what I said. If we get through it today, I'll keep it the same, depending on how fast we go. So we left talking about weighted means, right? So we have this example. We're looking at income, maybe by gender and race here. We said, how do we go through and calculate the weighted mean? Well, we're just going to kind of the mathematical way of writing this. I think I might have actually have these flipped from how I wrote it in the notes. So let me just to be kind of, right? So what we would do is go through every observation, multiply the weight by whatever value that group had for the X variable we're interested in. Because this is grouped data, we can't see each individual's income. And then once we add all those up, we'll divide by the sum of the weights, right? So if you think about this, and we kind of worked through that last class. So this sum of the weights, if I've got something like this, where I had this original data set, it had every single person, you know, Bob Smith, what their income was, what their race, what their gender was. Right? I can't see that data. All I can see is it grouped, okay? But that data existed. So once I see this group, it's kind of like when we were building histograms. Every observation should be in one of these categories, right? Now, you can kind of get into an argument about race classification, but just assuming that the BLF throws you in one of these categories, right? You have to choose one, then those frequencies should add up to what? Not 1, so you're thinking relative frequencies. Relative frequencies would add up to 1. Yeah, so these weights, right? These frequencies of each one of these categories, this will be the number of people that was in that original data set before it was grouped, right? So if we think about when we add up the weights, that's really just going to give us the total number of observations that was in that sample, or if we've got population data, the total number of observations in the population. So when we think about dividing by the sum of the weights, all we're really doing there is dividing by the total number of observations in the data that we can't see, right? The data before it was grouped. Okay? So we're talking about the weighted variance, right? It's going to be very similar to the kind of how we approach the weighted mean, like how we change the original mean equation to go to a weighted mean. Weighted variance will look very similar to the variance equation, but we've got to add in weights. Right? So just like we think about here was my regular mean, here's my weighted mean. But I said you can really think about the denominators. The sum of the weights was actually just total number of observations in that original data before it was grouped. So for the mean, it was giving us like the average value, right? Every single value was being weighted exactly the same, 1 over n, and we were getting kind of the middle point, the average value in that data set. When we went to the weights, we said, well, every single value for x, this variable x, each group might represent a different number of people. So we're going to have to weight that differently. Right? Same thing for the variance. The variance was an average deviation from the middle point of the data. Well, the middle point squared, but right. kind of, we're not as concerned with kind of that squares in the interpretation. So it's like the average deviation from the middle point of that data. But now if we've got group data, every deviation represents a different number of people. So when I go back here, I'll go forward a little bit. No, I don't want to break this down. So go back here. If I had some mean income for males, I think it ends up being like, I don't know, low 53,000 if I remember right. Well, the fact that 59 is 6,000 away from 53, that should carry a lot more weight in my variance because that deviation represents 73,000 people, as opposed to the deviation from 53 and 36, which is what, 17? That only represented 17,000. Right? So we're going to take those deviations from the mean squared, and just like we did with the mean, we're going to then multiply that deviation by whatever weight we have. And then the denominator, I wrote the number of observations there, but you could actually just think about, you wanted to write this out again, you could have the exact same thing in the numerator, but instead of n in the denominator, you could have the sum of the weights, right? Either one, those are going to be the exact same thing. Question? Fifth round? Thought I saw someone's hand, but not. So what does this look like, right? So try to break this down to steps, right? But what you're going to do is take that mean, like I said, it was around 53,000 for male income. You're going to look at that first group, right? The kind of racial category of white. You'll look at their value for X, 59,000. So you would take 59,000 minus that mean of 53,000, square that value, and then multiply it by the weight of 73,000 for that group. Write that number down, right? That is the weight times the deviation squared for that group. Now, in this example, these become ridiculously large numbers, right? So the ones that I'll give you are typically dealing with much smaller values, maybe not quite as interesting or applicable examples, but more doable, right? Not as easy to make a mistake when you've got what? 13 digits going on, right? So you go through and do this for every single group, right? You take the next group's value 38,000 minus that mean of 53,000, multiply it by its weight, is what? About 12,000, write that number down. So once you do that for every single group, you then add them all up. But why does this end up getting smaller? Well, because I add up these deviations squared times the weight, but then I still have to divide by the sum of the weights or the total number of observations and original data I couldn't see. So here, I would then divide by whatever these weights add up to. Any questions on that process? It's really the exact same process you were doing for the variance. The only added thing is you have to multiply that deviation squared by that group's weight. It's the only added step. So it's kind of like, once you've seen a weighted mean, the weighted variance, I think, makes a little bit more sense, like why it's the same thing, you're just throwing that weight in there. Okay? So if you wanted to, you could go through, I kind of just put a slide in here where I gave you the values. You can try to reproduce the same thing for female weight. Now, you have to go back to last week's slides. Those slides have the female mean, or you could calculate it again. Right, then once you have that mean, you would just go through, take the first group's mean income, take the first group's income, subtract the overall mean for women's income, square that deviation, then multiply by the weight. Do that for every single group, add them all up, and then divide by the sum of the weights for the females here. Questions, clarifications? So just an example. I put the regions one up there as well, just if you want to some more practice, you do just some different numbers and kind of check to make sure you can get the right answer. Right? Now, we'll kind of notice, we'll start out with the male, kind of female, and then I'll move to the regions, just to kind of point some things out more about what this variance, when it's a weighted variance, is telling us. So if we're thinking about the variance is going to be the average deviation from the middle point of this data. So if we're looking at this, right, for males, I said it was 53,000. Well, the value, so we're getting the average variance. So the group that's going to influence that variance the most is going to be the group that has the highest weight. Same kind of thing, the weights are pretty relatively the same for females here. But notice there's a much higher variation in kind of female income than there is, in male income than there is female income here, right? 94 million is much higher than 15 million. Okay? So what that's telling us is that, you know, we can look at the means. The mean for female income was significantly lower, right? But also there's less variation in that, right? So the female data is grouped closer to the center, which means it's less likely that we see females who are earning significantly low amounts, but it also means we see fewer females who are earning significantly high amounts when we compare it to the kind of the racial kind of variance that we see in male income. Okay. So, you know, if I'm looking at this, you can kind of say, if I'm thinking about the racial inequities of income, right? There's a lot more racial inequity when it comes to male income than there is female income, right? Race plays a smaller role in the variation we see in income with women as opposed to men. Now, do I have every single person in the country? No. I arguably break this down into more racial groups, yes. But this is the kind of general idea of how we can start to make comparisons. So when you have group data, right, it's not that there's just more variation in the original data because you can't see that. All you can see is the group data. So the variance is telling you, well, how much does the X variable, your income, how much does it vary across the groups? So these variance measures represent how much variation is there in income across racial groups, right? So we see it significantly lower for females than women. Any questions? Is that making sense, or at least trying to make sense? We'll kind of go to another one here. So if I'm looking at the region data, right, kind of a similar pattern follows, right? So if I'm looking at the variance measures, female income has much lower variance. So what would I say if I'm comparing the male variance to female variance here? What does it really tell me? That the variation in income for men is higher, but across what? It's not just in male income. It's the variation male income across regions, right? There's more regional variation in male income than there is regional variation in female income. Just like before, you're saying there's more racial inequity or variance across the races for men than there are for women, right? So when you change your category with these weighted variances, the interpretation is the variation of the data across the groups, whatever that group is. Before, it was across racial categories. Now it's across regions. Okay? Now, why that is the case, I don't know. I have to do a much deeper dive. My guess it has something to do with the types of jobs that men take across regions. Something about like you know, oil rigs or something like that. Probably playing a little bit of a role there, but that would be kind of the main idea. So that's how we can think about weighted variances, start to interpret them. Now we'll work through more in detail a weighted mean and a weighted variance example in a slightly different context, right? So I didn't dive too deep into the step-by-step for weighted variance. We will dive a little bit deeper here. I'll show you the kind of step-by-step. So the added wrinkle we're now going to fill in is that sometimes we see group data, and it's not grouped by a characteristic, but it's grouped into bins. So if I had something like this is like the satisfaction rating of some service. Those I forget the service industry that this data would pull from, something like, you know, hotel front desk or something like that. And they have cards, people respond to how satisfied were you, right? And they've got what, however many people this adds up to, it looks like it's about 50, 60 people, right, responded to these surveys. And they chose a satisfaction rating somewhere between 36 and 50. Right? So they grouped this data to say, okay, there was 25 people who responded with a satisfaction rating between 42 and 44. And you can only see integers here to kind of make the equalities easy, right? So this bin went from 41, you could only respond with 1, 2, 3, 4, 5, jumped right to 42. Made the equalities a little easier. So what does this look like? A histogram. Already, we've done this, right? We actually took data and put it into a histogram. Well, a lot of times, when someone takes data and puts it in a histogram, that's all they show you. You don't see the original data. You just see the histogram kind of table and then the chart that goes along with it, or the visual aid that goes along with it. So if I'm thinking about here, how would I calculate a weighted mean here? I can't see the original data. I can't see the original 50-some people and their individual responses. Well, here I'm interested in average satisfaction rating, so that becomes my X variable. The frequencies look a lot like what? Weights, all right? It just represents the number of people that responded with this value. The problem is this value is now no longer one value, it's 3, right? It could be 36, 37, or 38 for that first group. So what's maybe one way I could deal with this? If I need one value, and I have a range that goes from 36 to 38, just choose the mean, or the middle value, right? So not going to choose the mean, very close, we're going to choose the median, right? We want to choose the value that exactly is in the middle of that range for that group data. So we would choose what? 37, 40, 43, 46, 49. Those will be the values that we use for each group. That's the X values. And then we've got our weights, which are essentially going to be the frequency or the number of responses that were in each one of those ranges. Now, if I'm just looking at this, if you had to guess before actually going through, how would I find the weighted mean? 37 times 4, write that number down. 40 times 15, write that down. Do that for every single category. Then add up all of those X values times their weights. And then finally, once I add those up, divide by the sum of my weights or the frequency. So before we actually would do this by hand, if you had to just guess around where the mean is going to be, what would you guess? 43, right? If I'm thinking about what's the middle point of this data, right? That's still what a weighted mean is. It's where's the middle point. And the groups that have the most observations here is 42 to 44, right? So that midpoint of 43 is going to carry the most weight when I'm calculating that weighted mean. And then what are the next two most likely groups? Well, 40 and 46. And there's about an equal number. It's a little bit off, right? There's enough kind of to balance that out. So I'm probably thinking about it's going to be somewhere between 42 and 44. Now, what exactly is it? I probably can't give you, to a decimal what it would be, but I can kind of think, if I'm calculating this and I get 54, I made a mistake. Well, that doesn't make any sense, right? We talked about with the mean, it has to be somewhere between the lowest and highest value. You're looking for the middle point. So here we should see something between 49 and 37. So that highest and lowest midpoint. What about the standard deviation? Would you say it's going to be relatively high or relatively low? So let's just assume the mean is 43, right? Does this data vary a lot from that point? Well, this first group, their midpoint, is that going to vary at all from the mean? 43 minus 43 is 0, right? So this first group, if the mean was 43, provides evidence that there is no variation. Now, the other groups are a little bit further from that point, right? 46 minus 43 is 3, squared is 9. That's it's 19 observations, so it's going to carry some weight in that variance. So there are groups that represent there is variation in the data, and they do have a significant number of observations, right? We're picking up what the average variation is, right? And even after I square that, right? 3 squared is 9. It's not near as high as what we were seeing with income, which was like in the millions, or at least in the hundreds of thousands. So a lot of the times the variance, like I said, we can't compare across different data sets. The units vary. For income, it's very likely we're going to get differences from the mean of thousands of dollars. When you square that, it becomes really large, really quick. If I'm dealing with satisfaction ratings, and the groups are only 2, 3, maybe 5 away from that mean, even when I square them, it's still only 9, 16, 25. Just because of the units of the variable I'm looking at, that variance is going to be much smaller. Okay? So I'm looking at here, yes, there is some variation, but it's not that far from 43, right? Even the furthest away, so 49, what, 6 away from 43? But not only is that still only 36, right? 6 squared 36, it only represents 2 observations, right? So it's not going to carry near as much of a role when I look at that numerator, or it's not going to impact my weighted variance near as much when it only represents 2 people as opposed to 25 or some of the other categories. So we've got this mean. We can write it out a little bit different than we did before. It really doesn't matter. In practice, once we plug the numbers in, nothing's going to look different. We're just using the midpoints because we don't have a singular X value now. And our weights are just going to be the frequencies. But often our weights are frequencies anyway, so not a whole lot looks different here. In the past, I had mentioned we don't have to use all these frequencies. We can do something like the amount invested, or, you know, the percent of the overall grade. And so there, the weights might look a little bit different on frequencies. When it comes to the histograms, when we have group data by histogram, we're going to have the frequencies, right? That's what a histogram wants. Count ifs, right? Count the number of observations in this category. And then our variance is going to look very similar as well, right? We don't have any x values, we just have midpoints. So we're looking at the midpoints deviation from the mean squared. Same kind of idea. Once we plug the values in, it doesn't look any different. We're using frequencies as our weights. The only difference here is I've got n-1 here, right? So when we're dealing with histograms, a lot of times all we're going to have is sample data, right? So what we'll still do is take the sum of the weights. I'm going to write this out so we can maybe see this. So if I go sum of my frequencies, midpoint, mean. What I really want to do in that denominator, just like I did with the sample variance, is take that sample size minus 1. Right? That was the only difference between the population and sample variance. Same kind of thing if we're doing a weighted variance, but we know that histogram data, that satisfaction, that was just a sample of like 50 consumers. You know, there's way more people that bought that product or service. Then we actually want to divide by the sum of the weights minus 1. But once again, if we add those weights up, it should be the number of people that were originally in the data set before it was put into this histogram. So we can think about it as n-1 or the sum of the weights minus 1. Okay. And I won't try to trip you up on this when it comes to like an exam or something, especially when it comes to the weighted variance, right? I'll usually kind of specify like very clearly this is from a population data set or this is from a sample data set. Okay. Any questions on this? But just kind of taking things we've already talked about, right? Like we talked about the difference between the population sample variance, and it just shows up again when it comes to the weighted population or weighted sample variance. So if I'm looking at this, right? If I'm calculating the mean for this data set, what I'll go through and do is take that very first satisfaction rating midpoint, 37, multiply it by the frequency. Right, here I'm just calculating my weighted mean. Before I get to the weighted variance, I have to have the weighted mean. Well, I already erased it. So, sorry about that. Here was the mean. Here we kind of had, through my divided by sign, I'm a little too far. So we're going to go through again.
Would you multiply it as a percentage or as?
So we're going to use this as a frequency, right? So that's going to be our weight, right? So we won't like take 4 out of a certain number, right? We're just going to take that midpoint of 37, and that represents 4 people. So we'll take 37, multiply it by 4.
If it was a relative frequency?
You won't have to work with a relative frequency. Good question. If I had relative frequencies, it would become a little bit different, right? Because I said before, you could think about this as what you're really doing. How many people? We got 65 people total here. I'm writing this out using these numbers. The second group is 15. Because I'm multiplying everything, sorry, not multiplying everything, dividing everything by the sum of the weights, everything is going to be getting divided by 65 here, just adding up the frequencies. So if you wanted to use relative frequencies, instead of dividing by the sum of the frequencies at the end, what would the sum of, if I'm using, so let's say for my weights, I'm using relative frequencies, which is what I'm doing here, right? 4 out of 65, 15 out of 65. So instead of giving the frequencies, I was given the relative frequencies. These are my weights.
So you don't have to divide by anything.
What would the sum of the weights be? The sum of my relative frequencies should always be, someone said earlier, 1. So yeah, if I had relative frequencies, this actually becomes kind of easier because I don't have a denominator to worry about. If my weights are the relative frequencies, I know they'll always add up to 1, right? So that denominator, the sum of the weights, becomes kind of useless.
It's kind of like an out there question. But if you do that with a sample, how does that work?
How would you, it'd be harder to adjust it. You're correct. Because now So I've got relative frequencies. You have the sum of the weights here. You'd have to divide by, no, you'd still multiply by 1 over. If you were given the relative, it would be harder. You'd have to take the relative frequency and then change the denominator. Because what you would actually want in the denominator here, before I said you could think of it as we're dividing everything by 65. If I had sample data, now I'd actually have to adjust that proportion, those relative frequencies. Yeah, which would depend on the sample size, which is why often we don't use the relative frequency at the weights and we have the data like this. But you're thinking about this like in a good way. Yeah. But it would be more difficult. So it would actually be better to just back out your frequencies and then go ahead and calculate the weighted mean. I won't make you do that, but that would be what you do. So we walk through each one of these. I remember where I left off, but good question. Great. So we have the midpoint of 40. We multiply that by its frequency, write that number down. Do that for every single group, add them all up. What do we still have to do? Divide by the total number of observations, or the sum of the weights, sum of the frequencies here, which I have come down here at 65. So I've got the mean is exactly 43. These numbers worked out very nice because they're all integers. So now, if I'm going to go through and calculate the variance, how would I do this? Well, I go through to the first group, take its midpoint, 37, and then I'm going to subtract the mean, which we just found was 43. So 37 minus 43 is 6. Squared is 36. But then I have to multiply by the weight I'm using, which are now frequencies. So 36 times 4, 144. Then I go to the next one. Take its midpoint of 40. Subtract the mean of 43. 3, negative 3. Squared is 9. And then multiply that deviation squared by its frequency or its weight. 9 times 15, 135. Now, what's interesting is when I get to that third group, notice what's the deviation of this midpoint from the mean? 43 minus 43 is 0. So this group provides evidence that there is no variation. Now, it's just 1 out of 5 groups, so our variance won't be 0, right? But one of these groups provides evidence that there is no variation, right? So if we're thinking about once we had all these deviations squared times the frequencies, when we add them all up and divide by the sum of the weights minus 1, or n minus 1 here, it's going to give us kind of the average deviation from that middle point. Now, one of those groups provided evidence that there was no variation, but the variance is the average variation, right, across these 5 groups. So, we add up all those deviations, divide by the sum of the weights minus 1 here, because we had sample data, but we only had like 65 consumers out of however many we actually had over the whole year. And that's kind of the process that we would use. Any questions over any of those steps? Are we sure? We're just not sure what to ask, or making sense so far? Okay. So what if I wanted the standard deviation, weighted standard deviation? I haven't really talked about this, but what do you think probably the only additional step you'd have to do is? How did we go from a variance to a standard deviation before? Just take the square root, right? So I would just take the square root of 8.16. That easy, right? That's why I didn't have a slide on it. It's not really worth, right? Anytime we have a variance, whether it's a weighted variance, a variance of any other variance we talk about, to go from a variance to a standard deviation, you just take the square root. It's just scaling it one more step. Okay. All right. So now we're going to switch gears a little bit. Right? So that was weighted variance stuff. We thought about what if we have kind of bins. How do we deal with an issue like that? So now we're going to, I forgot this important. Right over. So now we'll talk about percentiles, which is the question you had earlier, right? Finding different quartiles and things like that. So you've probably heard percentiles talked about before. I don't know nowadays, since apparently it doesn't matter what you've done to get to college. You don't have to use your ACTs or SATs, which you can tell maybe my feelings on that. But if you do take them, you usually are told you're in this percentile. What percentiles are better? Would you rather be in the 99th or the 10th? 99th, because what does that say, really? If I tell you you're in the 99th percentile for your SAT score, what am I telling you? Smart, but how smart? Smarter than 99% of other people, right? So that percentile, all it's really telling you is whatever key percentile you're in, you're better than that percent of the other observation, of the other people that took the SAT, right? So said differently, it also means that I'm worse than 100 minus that percentile, right? If I'm in the 90th percentile, I'm better than 90% of the observations for other people that took the test, but I have a score that's worse than 10% of the other people, right? My score was the cutoff for where 90% of the data would be below it and 10% would be above. You can kind of think about like that's kind of like a median exactly split in half. Now we're just looking at different points, right? Not 50-50. We're looking at 90, 75, whatever. Hopefully things above 50, right? If we're talking about SAT scores. So this is the general idea. You know, I see a chart like this and like, I realize that there's percentiles talked about as early as like, you know, you can remember going to the doctor's office, they've always got these charts, tells you what percentile for height or weight you're in based on your age. I always say like, I think when I was 15, I would have been exactly 5 foot tall. So I was like below the 5th percentile, right? So not good, but like you can figure this out. So how did they come up with these lines? Okay. Like here's my 5th percentile. How did they come up with these values? So basically what they're doing is they had a bunch of data, right? Doctors are collecting information on children's heights and weights all the time. And so they throw them into a big data set, and then they arrange them from smallest to largest. Okay. So ascending order, smallest value to largest value. Okay. Then, if I wanted the 90th percentile, it needs to be the value that 90% of the observations are below it and 10% are above it. So how do I find what position that is, right? It's kind of easy if I think about if I had 100 observations. Well, if I range them from smallest to largest, whatever value's in that 90th position, better than 90% of the observations, worse than 10%. Kind of. It's not quite right, because once I take out that 1, now there's only 99. And so to calculate the position, that would give us the 90th percentile value, right? So just because I'm the 90th tallest person, if we're thinking about height, well, I need to know what the actual height is. That's that 90% cutoff, right? I can locate the position as the person in the 90th position, but what's that person's height? So the first thing we have to do is figure out where that position is in the data. So what we'll do is just take whatever percentile we're interested in, divided by 100. You can kind of imagine this is actually just kind of taking a percentage and converting it to a proportion. We'll then multiply that by the number of observations plus 1. So this accounts for the fact that once we find a value, it's like if I had 100 observations and I take out the 1, now I've only got 99. So we're kind of accounting, adding that 1 back in. You don't have to completely understand why. But this would be the equation that would give us the position of whatever p percentile we're interested in. The next thing we'll do is if this value is integer, well, that's great, right? If I get back that, the 90th percentile is in the 305th position, well, I just go to the 305th position, take that person's height, that's my 90th percentile. If I come up with a position that's like, I don't know, 16.3, right, depending on the size of the data set. Well, there is no 16.3rd position. There's a 16th and a 17th. So I have to do something that's called interpolation. Right? So I'll kind of walk you through this idea of interpolation here in a second. We'll actually you could actually do a lot of what we're going to do this semester. You can make it more complicated by adding interpolation, but it's important we understand what it is, even if we don't do it in every situation where we can, right? Sometimes we'll make it a little bit easier and we'll just find the mean, even though we know we're a little bit closer to one value. That might make a little bit more sense here in a second. So let's say I arrange the data, right? I've got some metal funds data. Not very interesting, but whatever. We just need a small data set to consider this. So I've got 10 different metals funds, and I've got kind of the change in value, right? Or the fund value. Right? So the first one went down by 56, whatever unit or whatever dollar amount this is in. And then we go all the way up to 76, right? So smallest to largest. If I want 25th percentile, right, I want the value that would be greater than 25% of these 10 observations, but worse than 75%, right? So if I'm guessing around where would that be? If I'm looking here, what position? Probably between 2 and 3. We got 10 observations. 25th percentile, probably in between that second and third. Right? But I can find exactly what it is, right? Using this equation. Right? So my sample size is 10. The percentile I was interested in was 25. If I go ahead and compute this, what I'll notice is because I'm pulling out that one observation of whatever position I'm in, it ends up being just a little bit different, right? Not quite 2.5th position, but it's a little bit higher. So the 2.75th position should give me the 25th percentile, at least from this data set. Well, there is no 2.75th position, right? So if I want the value that gives me that 25th percentile, well, I'm in between the second and third position, which means that that 25th percentile value should be somewhere in between -7.3 and 8. Right? Now, if I want the 2.75th position, what do you think is probably true about that value? Is it closer to 8 or to -7? Well, if my position equation tells me 2.75th position, that's a little bit closer to the third than the second position. So the value that will be the 25th percentile cutoff should be a little closer to 8 than it is to -7, right? We can't simply like take the average of -7 and 8 there. We need to weight the position that we're closer to a little bit more. So basically interpolation just becomes a weighted mean, right? So if I think about how I'm going to treat this, I know that I'm a little bit closer to the value in that third position. 2.75 is a little closer to 3 than it is to 2. So what I'm going to do is I'm going to use my decimal as my weight. So if I get the 2.75th position, that 0.75, that's going to be one of my weights. And the other weight would be whatever gets me to 1. It's almost like we're using relative frequencies. Yeah, we're not, but it's similar to that idea. We're going to have two weights because we're just in between two positions. But we know that we want to weight one of those values a little bit more. Which one? The value in the third position, because we're a little closer to that. So we'll use that decimal 0.75, weight the x value, 8.09, by that weighted 0.75. And then add to that, it's like calculating a weighted mean, whatever values in the position we're further from, by the smaller weight. Right? Well, so the weights will always add up to 1 here. We're going to have two weights. We look at the decimal to get the first one. The second one is whatever gets us up to 1. So when I divide by the sum of my weights, it would always be dividing by 1, kind of like we talked about earlier, if we use relative frequencies. So it actually becomes a little bit easier. Interpolation is like a weighted mean, but quite a bit easier. We're only ever going to have two observations. We can only be in between two values, and we have no denominator because our weights will always add up to 1. And this kind of makes sense, right? If I had the 2.75th position, let's say I had 2.5 was the position that would give me the 25th percentile. What would I have to simply do there? Each weight would be what? 0.5 for 50%. Think about percentages. Well, if each one gets multiplied by 0.5, what did we say when we have equal weights? That's just a regular mean, right? Everything was weighted equally. So if we did end up with 2.5, we'd just be taking the average of -7 and 8 there. We're not, so we have to do kind of this weighted mean, where the sum of the weights is always 1, which is a little bit easier than what we were looking at with those other weighted mean examples. So our values end up a little bit closer to 8 and a little bit further away from -7. Okay. Any questions on this? Is this making sense so far? I think I skipped the slide, so I'm gonna go back. Well, maybe we'll get to that one before we end today. So let's do I'll show you this in just about. I want to give you one more example. So let's say I end up and I got the 2.3rd position, right? So I'll just show you the metal funds just to remind ourselves. So let's say whatever percentile I want, I plug it in and I get it's in the 2.3rd position. I have to use the same process I did before. The decimal is going to tell me one of my weights. So 0.3. What would my other weight be?
1 minus 1.
Yeah, 1 minus that, or 0.7. So those are my two weights. But now, if I've got 2.3, what position am I closer to? A little bit closer to the second position than I am the third. So when I look at that value in the second position, it should be getting weighted by more. Well, which of these weights is more? 0.7, right? So I would do something like this. Now, When you have a position that's less than 0.5, I don't know why. It's counterintuitive, like screws with your brain. Because you look at this and you're like, oh, 0.3, that's how I get my first weight. So that's I'm going to weight, the value that I'm close. Well, no. The value you're closer to doesn't get weighted with whatever the decimal is. It gets weighted by the higher weight. When I have a position like 0.3, I identify the smaller weight first, actually, and then I'm identifying the larger weight. So you're kind of working in an order that doesn't seem to make as much intuitive sense. So I think that if you get a position that's like 2.8 or 2.9, it makes a little bit more sense. But if you follow the letter of the law, the rule is look at your decimal. That's one of your weights. You don't know which one it is yet, because if it's below 0.5, that's actually going to be a smaller weight, right? And so then the value you're further away is going to get further away from, sorry, it's going to get multiplied by that value. Okay? So everything kind of flips if that's the case. Now, if I do this, I should get a value that's a little bit closer to -7 than it is to that value of 8.09.
Wait, when does this flip, sorry?
Right, I was just saying, I always identify the first weight by whatever decimal I have with the position, right? So up here, I knew it was 0.75, and then I knew the other one was 0.25. Here, I know one of my weights will be 0.3. That means the other is going to be 0.7.
You always multiply the bigger number by whichever one is closest to.
You're going to multiply, whatever position, not whatever value is higher, whatever position you're closer to. So notice here, 2.3, you're closer to that second position, which is why the value in the second position gets multiplied by the higher weight of 0.7. Whereas before, we were closer to the third position, so the value of 8.09 is getting weighted. Yep. All right. Okay with that? Got one more thing we'll have on here. So you were asking about interquartile ranges earlier, and I have a question or two on these, but you'll see them in other classes, which is really why I'm showing you here. I don't like them a whole lot. They can be useful, but they're not the most interesting to me. But that's okay. You'll see them pop up, especially marketing. I think I see them a lot. So we now know how to find percentiles. So we're going to give some names to some. So the 25th and the 75th percentile, we'll call the first and the third. And then that 50th percentile, we'll call the second quartile. Right? Well, the 50th percentile should just be the same thing as the median. All right? So we can use this process, come up with a value for the 25th, 50th, and 75th percentile. We'll call those three things our quartiles. Okay? So what we're going to do, I don't know what these end up being. I'll choose some numbers. So let's say this is 30. This was my third quartile. Let's say my first quartile is 10. I don't know, we'll say 25 here, right? So have you ever heard of a box and whiskers plot in any of your other courses? So this is how you create a box and whiskers plot. You come up with each one of these quartiles based off the data. I just came up with these numbers to give you an example, right? We'll go through, find these three values and plot them, right? Here's my first quartile, second, and third, right? Notice the median here, or my second quartile, a little bit closer to that third, right? So that might tell me something about the skew of the data. We'll kind of punt on that for today, but I might return to that here on Friday to start the class. What you're then going to do is come up with these things called the interquartile range, which is just the difference between that first and third quartile, right? So out here, what would my interquartile range be? Well, if it's just the third minus the first quartile, 30 minus 10 or 20. Right? Does that make sense? Yeah. So that's my interquartile range. I then am going to come up with my lower and my upper limit. So how do I come up with this lower limit? Well, I'm just going to take my first quartile. I'm going to subtract 1.5 times whatever that interquartile range was. Okay. So I'm saying if I look at the middle part of the data, like I don't want the whole range because the whole range is really impacted by extremely large and extremely low values. The percentiles aren't as impacted near as much because I'm just looking at the location, right? The position. So I'll look at just the kind of range of the middle part of the data, right? Or between the third and first quartile. So here, if I take this, I get what? 10 minus, what would that be? 30. So I'm going to come up with like -20 here. I'm doing the math in my head correct. I think so.
Where'd you get the 10?
It's my first quartile value.
Oh,
right.
I wasn't sure if you did that. No.
Yep. No, I got you. So my interquartile range was 20. 20 times 1.5 was that 30. Now 20 minus 30. So that's how I'm coming up with that lower limit. Right? I then do the same thing, but I want to come up with an upper limit. All I do there, I'm running out of room. I take the third quartile and add 1.5 times that middle range, that interquartile range. So here I would have what? 30 plus 1.5 times 20, so 30 plus 30. My upper limit here, I don't know why I put these on different sides. I guess I hang out here. My lower limit was negative 20. My upper limit ends up being 60. So how do I use this box and whisker plot? So like I said, we can do some interpretation thinking about, well, if the first quartile is a little bit further away from the middle, it's probably telling me I've got kind of the longer left tail, right? That left tail is further away from that middle point. Okay? Now, with the upper and lower limits, that's really what I'm going to focus on today, which is the whole reason why we want to come up with this first third quartile. The box is interesting, but the whiskers are what's more useful. The whiskers tell us anything outside of these values, I can actually label as an outlier, and it's statistical justification for being able to exclude that. So I'll give you a really good example of when you could use this. I dealt with some alcohol use data once, and I had like the number of days you use alcohol a month. I had a 60 in there. I know that's bogus. There's not even 60 days in the month, right? Someone's just screwing with the survey person, right? But if I looked at the rest of the data, I could come up with an upper and lower limit, and that 60 was way above my upper limit, right? Because the majority of my data was like well under 30, right? 10 to, 0 to 20 was kind of the range there. So once I come up with that upper limit, if I see any data point above that, that's justification for excluding it from my data set. I know that it's something went wrong with it, especially with survey data. I get some really weird responses. Okay? So what we call this is the Q test, right? That if you have a data point that falls outside of this lower and upper limit, you can exclude it. You can label it as an outlier. And this is Q test justification, statistical justification for excluding it from your data set. And then you got the great meme, please don't reject me as an outlier because you are the Q test. The Q test rejects the outliers. Not that fun, but stats jokes really are. So this would be kind of how you come up with those different quartiles. You would build that box and whisker plot. We'll pick up, I think, doing correlation and covariance stuff. So that'll be the last questions on the Connect. So I will push that due date to the end of the day, Monday instead. But you should be able to get up to, I think it's the last 4 questions, and even parts of those last 4, you should be able to do parts of them. There's just a couple mentions of the covariance and the correlation coefficient, which we'll talk about on Friday. Okay? All right. So what are you guys going to try to do today for me? Actually, let's go back on and re-register your iClickers, and hopefully we can get it worked out. All right. And I will see you guys. Actually, I'll probably put up. I'm also going to put up a survey. It'll just be like I was making sure I want to see where you guys are at. If you get on and do it before we meet on Friday, we'll get 10 out of 10. Kind of like an online quiz, but it's just so I'm going to post it as soon as I'm done teaching in an hour, and it'll be due before we meet class on Friday. Right? So there's no correct answers. I'll give everybody 10 out of 10 as long as you do it. I just want to kind of get a gauge of where we're at. Okay? So you should see that pop up in about an hour. All right, I'll see you guys on Friday.